The air is just below freezing, and the pale limestone wall holds the first thin light of dawn above a slope of loose stone. Around you, the Alpine cirque is almost silent, except for a faint trickle of meltwater slipping somewhere beneath the rubble. The cliff looks still from a distance, clean and solid in the morning cold, yet its surface is lined with fine cracks, old seams, and quiet plains of weakness. In autumn, rain and thawing snow settled into those openings, sinking deeper than the eye could follow. Then the night cold returned, slowly, and the water turned to ice inside the rock. That small change was enough to press outward on the limestone, not all at once, but patiently, a little more with each freeze. By morning, a few sharp fragments have loosened from the wall and come to rest below, adding themselves to the pale fan at its base. Here in the high Alps, whole ridges and towers begin this way, with cold entering tiny spaces and widening them through many seasons. If you stay with this quiet wall a little longer, you can begin to hear how a mountain opens, one winter breath at a time. At first, the change is so small that it almost seems imagined. A splinter no longer sits flush in the wall. A narrow seam catches a darker line of shadow than it held yesterday. Near a ledge halfway up the face, a block the size of a table has begun to separate along an old bedding plane, leaving a gap fine as a knife edge, but real. That is the first escalation here, and it comes without noise. The cold has found a weakness that was already waiting inside the stone. Limestone like this was never a perfect mass. Long before it stood as a high alpine wall, it formed in warm ancient seas, layer upon layer of lime mud, shell fragments, and reef debris settling into thick beds. Later, pressure turned those beds to rock. Later still, uplift folded and raised them into the mountains. And all through that long history, the stone kept its memory of making, its bedding planes, its joints, its hidden partings, its fine fractures that now guide the water inward. So, if you want to understand why a few pale shards rest fresh at the base of the cliff this morning, the answer begins far older than last night's freeze. It begins in the structure of the wall itself. You can see some of it from here, even in dawn light. Thin horizontal lines run across the face, where beds were laid down in sequence. Vertical joints cut through them, dividing the cliff into columns and blocks. Other cracks angle away at quiet slants, making patterns that seem irregular at first, then slowly reveal a kind of order. Water does not enter the rock at random. It follows these inherited paths. It chooses the easiest descent, the seam already open a little, the fracture already linked to another, the tiny cavity where autumn moisture can linger after the surface has dried. And because it chooses those paths again and again, the wall begins to sort itself into pieces before any of them fully fall. This is why the cliff can look solid from a distance, yet behave like a patient puzzle being loosened from within. If I were walking straight toward the base now, I'd hear the rubble shift under each careful step, and I'd lose some of the pattern in the closeness of the stone. So I choose to stay back on the firmer ground of the cirque floor a little longer, where the whole wall can still be read. From here, cause and effect remain visible. A shallow groove channels meltwater from a snow patch toward a band of fractured rock. That band feeds a chute of broken fragments below. The chute widens into a pale talus fan, and the fan, spread over years and centuries, records what the wall has been giving away. Nothing dramatic is required, only repetition. As the sun rises a little higher, the uppermost edges of the limestone turn from blue-gray to pearl, then to a soft chalk white. But not every part of the cliff warms at the same pace. A buttress facing southeast begins to thaw first. A recessed gully beside it stays hard with cold. A narrow ledge catches light for perhaps an hour in the middle of the day, while the crack just beneath it remains shaded almost until evening. That uneven rhythm matters. On a mountain like this, freezing and thawing are not shared equally. One fracture may fill with water by day and freeze again after sunset. Another, sheltered from sunlight, may remain sealed with ice for much longer, holding pressure deeper in the stone. A third may open only in spring, when melt from a lingering snow patch seeps down into a network of older joints. The wall is one cliff, but it does not live by one clock. It keeps many small climates at once. This is where the mountain's shape begins to emerge from weather, not in broad strokes but in differences. The warmer ledges release water that can travel downward. The colder gullies preserve it as ice. Corners and protrusions lose heat more quickly than thicker masses of stone. Blocks already bounded on several sides by joints become especially vulnerable because the cold can work on them from more than one direction. So over time, some parts of the wall loosen faster than others. A rib stands out, a recess deepens, a line of weakness becomes a groove, then a chute. What seems like scenery is also process. The cirque is quietly organizing itself. If you listen long enough, even silence becomes evidence. There is no crash this morning, only a dry tick from somewhere high on the face, as a grain or chip shifts free. A few seconds later, a faint skitter runs down the rubble below, then stops. That small sound tells you the cliff is active, though not hurried. A fragment has detached. Gravity has taken over where frost left off, and the loose stone below has accepted another piece into its slow accumulation. The science of it is simple at first, and then more subtle the longer you stay. When water freezes, it expands. Inside a confined crack, that change can press strongly against the rock walls. But in the Alps, frost weathering is not always a single clean event of water turning to solid and forcing the crack apart like a wedge in timber. Often it is a slower set of conditions, repeated over many nights and days. Moisture enters a fracture. Temperatures move around the freezing point. Thin films of water migrate toward growing ice. Ice lenses can develop in tiny pore spaces and openings, drawing in more moisture from nearby zones that have not yet frozen. The pressure builds not only from one moment of expansion, but from the way ice can continue to gather where the thermal conditions favor it. That patient process matters in limestone, especially where the rock is already crossed by joints and bedding planes. The stone does not need to shatter in one night. It only needs to be persuaded a little more each season to let go along the lines it already contains. And this wall is full of such lines. You can trace one diagonal fracture from a notch near the top, all the way down to a shelf where snow often lingers. Below it, a run of fresh, angular blocks lies brighter than the weathered stone around them. They have not yet been darkened by lichen. Their edges are still sharp, their surfaces still carry the clean, powdery whiteness of newly broken limestone. That brightness is another reveal. Some of this debris is recent. The fan below the cliff is not only ancient inheritance, it is being renewed. Each winter adds to it, each thaw rearranges it, each new fracture in the wall sends a future fragment toward the slope. The process is easy to miss if you visit once. It becomes unmistakable if you stay. So you stay. The morning widens slowly over the cirque. Across the basin, another wall rises in terraces and pale buttresses, but your attention remains here, on this nearer face where the workings are clearer. A line of darker moisture marks a seam that must be connected to something deeper. Even after the surface chill, water still threads from it in places, seeping out where an inner crack meets the air. That means the wall is not merely wet outside. It is carrying water within, and once water occupies the rock this way, the next cold night can reach farther than before. The mountain is not a barrier keeping weather out. It is a volume through which cold and moisture negotiate. Sometimes the negotiation favors stillness. Sometimes it favors release. By late morning, the sun has touched more of the slope, and the contrast becomes plain. The south-facing ledges show a gentle shine where frost has softened into melt. The shaded chute remains dull and dry-looking, though it likely holds old ice just beneath the surface. This split condition creates a new development. Meltwater from the warming ledges begins to travel toward colder fractures lower down. In other words, one part of the wall is feeding another. What thaws above may freeze again below. That transfer is one reason certain cracks widen faster than their neighbors. It is also why the cliff starts to divide into forms. A tower remains where joints are widely spaced, and the mass between them is thick. A cleft deepens where water repeatedly descends and refreezes. A ledge broadens as small pieces are plucked from beneath it. The same winter day can strengthen one shape and weaken the next. Over many years, these slight imbalances create the architecture of the mountain. Seen this way, frost wedging is not only a force of breakage, it is a force of selection. It decides, slowly, what remains standing and what becomes slope. There is a place near the center of the wall where three fractures meet. From below, the junction looks almost decorative, like lines drawn in charcoal across pale plaster. But that meeting point is important. It defines the corners of a block already loosened on several sides. Autumn water entered there easily. Winter cold reached it from more than one exposed face. And now, after many cycles, the block holds itself by less stone than it once did. Not by nothing. Not yet. But by less. That distinction matters in mountain weathering. The dramatic moment of separation arrives late. The true work happens earlier, in all the quiet reductions that prepare for it. A listener at the wrong hour might think the rockfall was the event. Standing here, you understand that the event has been underway for months, perhaps for decades. Even the fallen fragments below tell that longer story. Some are fist-sized, fresh and angular. Some are larger slabs, their flat faces echoing the bedding planes above. Some have begun to crumble at the edges under further frost, or have been split again after landing. The talus is not just discarded material, it is an archive. Its sizes, angles, and arrangement reflect the wall that produced it. Its newest stones lie atop older fans. Its channels and ridges show where fragments bounce, slide, or come to rest after snowmelt has altered the slope. And beneath the visible surface, cold air and moisture move through the voids between blocks, continuing the work below ground level. Breakage does not end when stone reaches the base. It changes setting. This is why the loose slope sounds hollow in places. Between the blocks are spaces large and small, hidden from view, where air lingers cold and meltwater can slip down out of sight. During parts of winter, snow may cover the talus while cold remains trapped inside it. In spring, water enters from above and refreezes in shaded pockets. Fine fragments settle into gaps. Larger blocks shift imperceptibly as support beneath them changes. The mountain continues to open even after pieces have fallen away. The wall and the slope are not separate chapters. They are one connected machine of stone, temperature, water, and time. As noon approaches, a soft warmth reaches the cirque floor, though the air still holds that high alpine sharpness. Tiny threads of melt begin to appear more clearly at the foot of the rubble. They vanish under the stones almost as soon as they emerge. That vanishing is another clue. The broken limestone is porous as a landscape, even where the rock itself may not be porous in every layer. Water can disappear into spaces opened by fracture. It can travel unseen for a while, then return lower down. And every hidden route it takes increases the number of surfaces available to frost. A smooth wall offers one face to the weather. A fractured wall and a broken slope offer thousands. So the more the mountain opens, the more opportunity cold has to enter again. This is the quiet feedback at the heart of the cirque. Frost wedging creates debris. Debris creates voids and pathways. Those pathways carry water. That water finds new freezing sites, and the process deepens its own reach. By early afternoon, the first warmth begins to leave the highest points again. The sun shifts behind a ridge. Shadow pours slowly down the wall, ledge by ledge. What thawed a few hours ago will soon cool. Any water left in the finer seams will feel that change first. You can almost sense the decision the mountain does not make consciously, but enacts all the same. Keep the water at the surface, where it may evaporate or run off, or draw it inward, where the coming cold can turn it into pressure. Because the cliff is fractured, because the beds dip just so, because the joints connect in hidden lines, the second outcome happens again and again. The structure guides the process. The process exaggerates the structure. And every season, the wall becomes a clearer expression of the weaknesses it inherited. That is how an entire limestone mountainside begins to sort itself. What looks random from far below is often profoundly organized when read through its fractures. A couloir forms where breakage is concentrated. A stack of ledges persists where certain beds resist a little longer. A freestanding tower emerges where joints isolate a mass faster than surrounding stone is removed. The mountain is not being ruined, it is being articulated. Its hidden design is becoming visible, and below that visible wall, the slope waits to receive what the next cold night loosens. By late afternoon, that next cold begins to gather almost before the eye can see it. The sunlight thins on the upper ribs of limestone, and the brighter ledges lose their shine. The seep lines that glimmered at noon become dull again, as if the wall is drawing its moisture inward. This is one of the quiet decisions of the slope. Water does not remain where it is warmed. It follows gravity and stone texture and the smallest connected route. A thin runnel from a melting patch crosses one shelf, enters a crack no wider than a fingernail, and disappears. Another thread slips beneath a loosened slab where the rock has lifted by only a few grains of width. There, in that hidden contact, cold has an advantage. The evening air cools exposed surfaces first, but inside a narrow fracture, the temperature can hold near freezing for long stretches. That narrow range is important. Frost weathering often works most effectively not in severe cold alone, but in places that hover around the freezing point, where water can still move, then freeze, then draw in more moisture. So the mountain settles into an hourly rhythm. The sun leaves one buttress, a shaded groove preserves old ice, a damp seam meets fresh runoff from above. The pieces come together with no need for spectacle. You could stand here all evening and notice almost nothing changing. Yet within the stone, change becomes more likely with every degree the air gives up. The block with the knife-edge gap is a good example. In morning light it seemed merely outlined. Now, as the wall cools again, the gap darkens sooner than the rest of the face. That tells you it has depth. The opening is not a surface mark. It has become a small chamber for moisture and then for ice. If the bedding plane behind it is smooth enough, and the vertical joints at its edges are connected, the block is no longer held by a continuous mass. It is held by bridges, tiny intact links of stone. Each freeze tests them. Each thaw wets them again. Each season leaves fewer of them to carry the weight. This is how a wall that looks unchanged from year to year can, in truth, be reorganizing itself. The process does not need to be visible every day. It only needs to be cumulative, and in high limestone country, cumulative change is often the most important kind. The Alps provide long winters, frequent passes across the freezing point, snow that melts and refreezes, and a rock type already divided by bedding and joints. That combination makes certain cirques and cliffs especially responsive to frost action. Not everywhere equally, not every face in the same way. A shaded north wall may preserve snow late into summer, feeding seepage into fractures for weeks after nearby slopes have dried. A south-facing wall may experience more frequent daily thaw and nightly refreeze in early winter and spring. A gully may collect drifted snow that melts slowly against the rock. A projecting buttress may dry faster and resist some kinds of cracking, even while losing fragments from its exposed corners. These differences are why one slope becomes a talus field of fine angular rubble, while another nearby holds larger slabs and more intact ledges. The same mountain contains many versions of the same process. As the temperature falls through evening, one of the most important changes happens out of sight. Liquid water in the smallest openings begins to migrate. Ice does not simply appear everywhere at once. It grows where conditions favor growth, and as it grows, it can draw thin films of unfrozen water toward itself. In fine cracks and pore spaces, this matters greatly. The result is pressure that can continue beyond the first instant of freezing. For limestone, already divided by planes of weakness, that sustained pressure can be more significant than one brief snap. It turns a hairline crack into a working fracture. It pries open the edges of beds. It detaches flakes from exposed surfaces. It helps convert internal weakness into external form. So when people speak simply of water freezing and expanding, they are not wrong. But the mountain's full story is gentler and more intricate. Cold does not act alone, it acts with moisture supply, with thermal gradients, with rock structure, with time. And time, here, is generous. The cirque has no need to hurry. Night arrives and the wall begins another cycle. From the meadow edge, where sparse grass stiffens with frost, the talus fan takes on a bluish cast. Its upper stones are large and sharp, recently fallen enough to keep their clean edges. Lower down, where the fan broadens, smaller fragments mingle with older weathered material, and a few hardy plants occupy pockets where finds have collected. Even this sorting has a pattern. Large blocks tend to stop sooner on rougher, steeper parts of the slope. Smaller pieces can work farther down, slipping between gaps, settling after melt, or moving with slushy snow during spring release. Over many seasons, the fan grades itself. Not perfectly, but enough to tell you that gravity is shaping what frost provides. The slope is not only a pile, it is a record of transport. Listen now. In the first real cold of evening, and the sounds become more selective. A tiny ping from high on the wall, then nothing. Later, a skitter on the scree, too light to mark a major fall. Then stillness again. Those are the sounds of preparation more than collapse. The mountain is loosening pieces into readiness. Some will fall tonight, some next month. Some may remain outlined for years before finally separating. Delay is part of the process. The cliff does not respond like glass. It responds like a jointed, bedded rock mass under repeated stress, where failure travels along inherited planes and often pauses at irregularities. This is why frost wedging produces architecture rather than chaos. The limestone does not break at random points with equal ease, it follows its structure. Where bedding planes are thick and coherent, walls can remain broad and pale. Where beds are thinner, more fractured, or cut by intersecting joints, the rock steps back into ledges and recesses. Where a series of vertical joints isolates a narrow strip, towers can begin to stand out from the parent wall. Where frost opens a chute, later fragments are more likely to travel that same path. The landscape grows more legible as it ages. By moonrise, the cirque feels larger. The dark between the walls deepens. A line of late snow above the cliff gives off a dim sheen, and beneath it the limestone becomes almost luminous in its own way, pale against the cold sky. At this hour, the mountain seems most still, but this is often when the interior work becomes most effective. Water tucked into fractures across the afternoon now meets a fresh drop in temperature. Thin films freeze, ice bodies grow, pressure is transferred to the crack walls. If the fracture is partly closed, the force is concentrated. If the fracture connects to a wider void, water may continue to move inward before freezing deeper in. Not every crack experiences the same stress. Some are too open to build pressure efficiently, some are too dry, some are sealed by previous mineral deposits. Others are perfectly placed, connected to moisture, and exposed to the right thermal rhythm. These become the active lines. And once a line becomes active, it tends to remain important, because every small widening increases its ability to accept more water the next time. That is another form of selection. The mountain is choosing pathways through the simple logic of physics. The most effective cracks are used again, the least connected are abandoned. A wall that once held countless possible weaknesses gradually emphasizes a smaller network of working ones. From those, the larger shapes emerge. Toward midnight, a fragment finally gives way. You do not see it. You hear the brief, dry release, one knock against the wall, then a scatter across the upper fan, then silence. No drama lingers after it. A stone the size of a loaf has detached from some hidden ledge and joined the rubble. By dawn, its fresh face will show almost white among the older grey surfaces. It is a small consequence, but a clear one. The cycle has produced another visible result, and because the slope is steep, that fragment may not stay where it first lands. Spring thaw may shift it lower, Another fall may strike it and split it again. Snow creep may nudge it a hand's width down slope. A heavy melt may wash fines from beneath it and let it settle. So even after separation, the story remains open. Morning returns slowly, the cirque brightens from above, and the limestone wall resumes its soft pearl tone. On the talus fan, the newest stone stands out exactly as expected. Nearby, a few chips, no larger than coins, lie around it. They may have fallen with the larger fragment or broken from it on impact. This is how evidence accumulates here, not as one grand scar, but as many small proofs placed among each other. The fresh fragment tells you something else as well. Its break surface is not random. One side is smooth enough to reflect the bedding plane from which it parted. Another side is rougher, where the fracture crossed the grain of the rock and encountered tiny variations in texture and cement. That mixed surface shows two structures at work together. Part of the detachment followed a pre-existing line. Part required new breakage. Frost wedging often acts this way. It exploits old weakness, but it also links weaknesses together, making a continuous failure from discontinuous lines. In other words, it edits the rock. It does not invent the limestone structure from nothing. It reads that structure, then enlarges what can be used. As days pass into early winter, the pattern becomes more obvious. Snow arrives likely at first, thin enough to reveal the shapes beneath it. A dusting clings to ledges, outlines blocks, and settles in recesses where wind cannot lift it away. Against the white, the active fractures darken. Some remain open enough to show through as clean lines. Others are filled flush with snow, making hidden channels that mark where water and cold have access. This is one reason geologists and mountain observers learn so much from first snows. They reveal topography at a fine scale. They show where the wall is smooth. They show where it is deeply jointed. They show where ledges collect drift and where rockfall strips snow off again. Even the shape of retained snow can hint at future movement. A shallow niche that holds snow against the rock all winter may feed seepage through spring. A cleft that traps blown powder may preserve cold into warm months. Both can become engines of continued weathering. In this way, winter is not only a season of force, it is also a season of storage. Snow stores water, talus stores cold, fractures store both moisture and the memory of past opening. Then spring redistributes them. But before spring comes, the cliff spends many weeks in repetition. Freeze, partial thaw, freeze again. Perhaps a warm wind one afternoon, perhaps clear hard cold the next night. Every variation matters, though none announces itself loudly. A south-facing shelf may drip for 2 hours before dusk, sending water into a shaded seam below. A narrow chimney may remain packed with old snow, cooling the rock around it even on bright days. A slab exposed on 3 sides may contract more rapidly than the mass behind it, helping a crack widen just enough for water entry. Cause and effect keep layering. No single event explains the shape. The shape is the sum of favorable moments, and because those moments recur season after season, their effects become dependable. The cliff begins to sort itself into a more definite arrangement. Some blocks remain locked, some are nearly free. Some ledges lose thin sheets from their fronts, creating slight overhangs. Below, certain channels in the talus fan become preferred paths for moving stone. When new fragments fall into them, they run farther. Where the slope flattens, deposits build into low ridges. Where rough larger blocks obstruct movement, smaller shards collect behind them. The lower body of the mountain starts to mirror the upper one. Above, fractures define potential pieces. Below, gravity sorts the pieces by size, angle, and root. This is the point where the story moves naturally downward. The wall has shown how separation begins. Now the slope begins to reveal what separation becomes. Step off the firmer meadow margin and onto the talus itself, and the mountain feels different underfoot. The sound changes first. Grass gives a muted spring, loose limestone gives a dry shifting answer, a short grind, a hollow clack where one block meets another. The fan is steep enough that every step asks for care, yet it is not unstable in any dramatic sense. It is a place of many settled motions. The uppermost stones are angular and pale. Some rest with wide, flat faces tilted upward, like pages left half open. Others stand on edges, propped by neighbors, their positions temporary in the long scale but calm in the moment. Between them are dark voids where cold air lingers. These spaces matter as much as the stones. Talus is not merely broken rock spread out on a slope. It is a porous body. Air moves through it. Water moves through it. Snow enters and melts within it. Fine sediment filters down through its gaps. Roots, where they can, search its edges. This means frost wedging does not stop at the base of the cliff. It changes mode there. A block that lands intact may later crack along a bedding plane as water freezes in its own surface seams. A shard may split again because night cold reaches both exposed faces, while moisture remains trapped in the center. A cavity between stones may preserve ice after the surface has thawed, then meltwater from above can refreeze in that hidden pocket, shifting support under nearby fragments. Small adjustments follow, nothing theatrical. A stone settles by a finger's width. A finer wedge of debris slips into a lower gap. The upper block loses support and rotates slightly. On a mountain slope, these little changes are enough to continue downslope migration over years. This is why talus fans slowly creep outward and downward, even without large rockfall events. Gravity does patient work too. After a storm, the fan gives you fresh evidence. Imagine snow falling wet against the warm edge of a brief thaw, then freezing hard overnight. The next day, sunlight softens the snowpack just enough for water to sink into the upper rubble. That water reaches cavities still below freezing. Ice forms around contact points between stones. Later, when thaw returns, some bonds release while others persist. The balance of support has changed. A few blocks settle. Small stones run down into the spaces opened by their movement. By the time the snow is gone, the fan is not where it was before. It has reorganized itself by increments. This is one reason Alpine scree often looks both chaotic and strangely ordered. The arrangement is constantly renewed, but according to simple rules. Fragments fall from above. Larger ones tend to stop sooner. Smaller ones travel farther. Voids open. Fines fill them. Water finds channels. Freeze and thaw alter support. The result is a surface of many irregular stones, yet with an overall fan shape that remains recognizable for centuries. Look back up from midway on the slope, and you can read those centuries in reverse. The chute above points to a source area where repeated detachment has focused falling debris. To either side, more intact buttresses stand over narrower aprons. A rib with fewer obvious joints sheds less material. A recessed section, heavily cut by fractures, feeds a broader spread of blocks. The geometry is clear. Structure in the wall becomes pattern on the slope. This is one of the most elegant consequences of frost wedging in limestone landscapes. The process is local, acting in tiny cracks, but its results are large enough to organize whole mountainsides. A cirque floor that might otherwise hold continuous meadow becomes interrupted by pale stone rivers. Those stone rivers are talus tongues and scree runs. They descend from cliffs in lines that reveal where weathering is most active. Between them, gentler areas collect soil and support grass, alpine flowers, and low shrubs. The mountain begins to divide itself into habitats according to where rock continues to arrive. Talus is harder for plants to colonize, especially in its upper active reaches. The constant small shifts, the lack of fine soil, and the rapid drainage all limit what can settle. Just beside it, where debris has thinned and finer material has accumulated, life can take hold more easily. So frost wedging shapes not only stone forms, but the very pattern of living ground. Still, for now, the talus itself remains the focus. Kneel beside one larger block, and you can inspect the signs of its journey. Its upper face is newly clean, but one edge already shows powdering where tiny crystals in the limestone matrix are beginning to loosen. A thin seam runs across it, likely inherited from the bed it came from. If water enters that seam through winter and spring, this single block may become two. Nearby lies a flatter slab whose underside is darker. It has been resting against damp sediment or snow longer than its exposed top has. Turn your attention lower, and the stones become smaller on average. Not universally, because large blocks can travel surprisingly far if they bounce well or descend over snow. But the overall tendency remains. Sorting acts over time. That sorting gives scree slopes their texture. Upper fans are rough, open, blocky. Middle zones mix slabs, angular cobbles, and smaller chips. Lower margins blend into finer rubble and soil, especially where water slows or vegetation begins to trap sediment. Each part records a slightly different balance between supply and movement. In narrow couloirs, the arrangement tightens further. A couloir is a steep gully, often bounded by walls, where falling debris becomes focused into a confined track. Because the sides limit lateral spread, fragments here travel in more concentrated lines. Snow often persists in these channels. Meltwater runs through them. Cold lingers. That makes couloirs especially important in high limestone terrain. They are both conduits and workshops. Rock enters from the walls. Snow cushions or redirects its descent. Water vanishes beneath the rubble. Frost acts within the fill as well as in the bounding rock. Over time, the couloir deepens as an organized feature, not because one tremendous event cuts it, but because countless small detachments feed the same route. Stand at the edge of one, and the shape becomes obvious. Its floor is choked with angular stone. Its sides are scarred by small, fresh breaks and older, weathered faces. The rock there often appears brighter than on neighboring walls because new surfaces are exposed more frequently, and lichen has less time to spread across unstable sections. This brightness is another useful sign. Freshness in a limestone landscape often reads as pale color. Age reads as darkening, staining, and biological cover. Where frost wedging remains active, brightness returns repeatedly. Now descend farther to where the talus fan reaches the cirque floor. Here, the slope softens. Snowmelt threads out from beneath the stones in several narrow rills. Some vanish almost immediately into the rubble. Others continue a little way across finer sediment before sinking. The water is cold enough to numb a hand quickly, but its movement is gentle. And its disappearance tells you something important. The limestone landscape is becoming not just fractured, but connected. Water no longer flows only over the surface. It slips into the mountain's broken skin. This matters because hidden flow extends weathering below what the eye can follow. At the toe of the fan, fine material accumulates in sheltered spots. Some of it comes from the direct crumbling of limestone into smaller grains. Some comes from dust blown in from elsewhere. Some is organic matter, the first dark trace of plant life catching among stones. Together, these finds begin to create a more stable substrate. A tuft of grass roots there. A moss patch darkens the shaded side of a block. A tiny seedling establishes itself in a pocket no larger than a hand. Even now, while rockfall still feeds the upper fan, the lower margin is beginning a different chapter. The mountain gives away stone above. Below, time turns some of that stone towards soil. But the transfer is uneven. Some pockets on the lower edge of the fan stay almost still for years, while a strip only a few steps away keeps receiving fresh stone every spring. That difference begins with how the cliff above is divided. A broad wall cut by many open joints sends debris often. A more massive rib sends less. Snow also changes the pattern. Where winter drifts build deeply against the base, they can cushion falling fragments, hold them in place for a season, and then release them lower when thaw comes. So the same slope can hold both movement and rest, both fresh brightness and slow darkening. If you walk across that lower margin in late summer, the contrast is easy to read. Near the active tongue, blocks are clean, angular, and loosely fitted. A little farther aside, lichen has begun to spread in grey and pale green films. Dust has gathered in cracks between stones. The first rooted plants are no longer isolated by chance, but repeated in a pattern that follows shelter, moisture, and finer sediment. This is where the mountainside starts to show a new kind of evidence. The rockfall path is still there, but around it the surface is being edited by quiet accumulation. Wind-blown grains settle. Decayed plant material darkens the hollows. Spring water leaves traces of silt where it slows. Every one of those additions changes how the next season's water will behave. A bare slab sheds moisture quickly. A shallow pocket of fines can hold it a little longer. Held moisture means a longer cool period after sunset. It also means more opportunity for freezing in tiny openings, not only in bedrock, but in the fallen blocks themselves. So the lower fan is not simply where motion ends, it is where motion becomes more selective. Some stones continue downward, some split where they lie. Some help trap the very material that will one day soften the edge of the scree into meadow. This is one of the quiet reversals in Alpine limestone country. The same frost that breaks cliffs can also help prepare the small sheltered places where life takes hold. Before the plants become important, though, the stone changes again. Look closely at a limestone block that has rested in place through several winters. Its corners are still angular, yet no longer sharp in the way a fresh break is sharp. A few edges have flaked, a thin face has peeled from one side along a bedding surface, a small seam has widened enough to catch dark moisture after rain. The block is beginning to weather as a miniature cliff. It has upper and lower faces, wet sides and dry sides, sunlit plains and shaded seams. Each side lives by a slightly different clock. That matters because frost wedging on a mountainside is never confined to one dramatic wall. It spreads through scales. The cliff breaks into blocks. The blocks break into slabs. The slabs break into chips and grains. At each scale, water seeks openings, and cold favors certain ones over others. What you are seeing on the fan is the same process translated downward into smaller forms. This is why the scree often seems alive with structure even when nothing is moving at that moment. Each stone carries the geometry of the wall it came from. Flat pieces reflect bedding planes. Column-like fragments reflect joints. Wedge-shaped pieces record where two fractures met. And as they settle together, those inherited shapes influence how stable the pile can be. Flat stones lie and stack. Angular ones prop one another above hidden voids. Fine shards sift downward. The fan sorts itself mechanically, one slight adjustment at a time. Now imagine this slope through a sequence of seasons. Early winter opens the first fractures in the wall and chills the talus from above. Midwinter stores snow in couloirs and cold in the voids between stones. Late winter and spring release meltwater, which enters both cliff cracks and rubble gaps. Summer dries the exposed surfaces, but not evenly. Deep hollows stay cool. Shaded seams keep a trace of moisture. Autumn rains return, and the cycle begins again with a fresh supply of water. By the time many such years have passed, the lower body of the mountain has become a broad machine for receiving, sorting, and passing on stone. It is not hurried, but it is not idle. One narrow tongue of debris running down from a chute tells the story clearly. High on the wall, repeated frost action loosened fragments along a connected fracture zone. Those fragments fell into a confined route. Snow in winter guided some of them, spring melt reworked others. At the fan margin, smaller pieces spread wider, while larger blocks stopped sooner. Fine material settled in the quieter flanks. Plants colonized those flanks first, then roots, moisture retention, and additional frost action began working on the margins of the deposit itself. A line that began as fracture in rock has become form in the landscape. Follow enough of those lines across an alpine cirque, and the whole basin starts to make sense. The meadow is where enough vines have gathered and enough stability has persisted. The scree is where delivery of fresh stone remains steady. The couloirs are where concentration is strongest. The pale towers above are where the wall has stayed standing between the active lines of weakness. This is why a limestone cirque can feel both orderly and broken. its pieces are arranged by process. Even the places where water disappears into the debris begin to matter more now. At the foot of the fan, a thin thread of melt slips into a gap and is gone. A few meters lower, another thread emerges beside a moss-darkened stone. This is a small sign, but a meaningful one. The slope is no longer behaving only as a surface. It has internal pathways. Those pathways are temporary in detail, because a shifted block can alter them. But in a broader sense, they become more established over time, especially where debris rests against fractured bedrock below. Water entering there may continue through loose stone, then into widened joints in the mountain itself. That is where the story starts to turn. Until now, most of the visible action has involved the opening of the cliff and the growth of the scree. But limestone has another quality that becomes more important once fractures widen and connect. It can be dissolved, slowly, by slightly acidic water. Rain and melting snow take in a little carbon dioxide from the air and from soils. That makes the water weakly acidic, not strong enough to seem harsh or dramatic, only strong enough over long spans to enlarge pathways in carbonate rock. Freshly broken limestone offers new surfaces. Frost wedging provides those surfaces constantly. So mechanical weathering and chemical weathering begin to cooperate. The mountain has been opened from above. Now water can begin to reorganize it from within. On a broad limestone pavement higher in the cirque, where the bedrock lies exposed between snow patches, the first signs are delicate. The rock surface is crossed by narrow grooves and slots. Some follow old joints. Some are guided by tiny irregularities where water lingers. Between them stand strips of intact stone, as if the pavement has been scored into blocks. These are the beginnings of grikes and clints, the split texture common in Karst limestone country. In the high Alps, frost often helps prepare them. A joint widened by ice can catch more meltwater. A crack freshened by breakage presents reactive mineral surfaces. Water enters, flows, dissolves a little, and returns again. Year after year, the opening deepens. This change is subtle at first because the mountain still looks dry and pale from above, but the behavior of meltwater reveals what the eye alone cannot. Where a smooth slab once sent water across the surface in a visible film, a widened joint now swallows it. A thin rivulet reaches a seam and vanishes. A shallow hollow fills briefly after rain, then drains downward without any obvious outflow. That disappearance is the new development. The water has learned the mountain's openings, and once it enters, it can do more than freeze. It can dissolve, it can carry calcium and bicarbonate away in solution, it can widen the route just enough for more water next time. This is how frost wedging begins to merge with karst development. One breaks and opens, the other enlarges and connects. Together they turn a wall and slope into a porous terrain. You can trace the shift best after a bright spring day. Snow patches shrink back from the limestone pavement. Every exposed channel shines briefly with melt. Then, little by little, the surface flow shortens. Water reaches fractures and disappears before crossing the whole slab. At some points the openings are still hairline and easy to miss. At others they have become slots wide enough to gather dark soil in their depths. Those slots often hold the lost snow too, because they are shaded and protected. That lingering snow feeds prolonged seepage, which in turn feeds both frost weathering and dissolution. Again, repetition is what matters. The mountain does not suddenly become karst. It grows more karst-like wherever frost has opened effective routes for water entry. Consider one fracture near the edge of a ledge. At first it was only a joint, perhaps inherited from uplift and stress long before this cirque took shape. Autumn rain entered, winter freezing widened it slightly, a slab detached beside it, exposing fresh stone. Now snowmelt reaches the joint more easily. Slightly acidic water trickles into the crack. Calcium carbonate begins to dissolve along the walls. The opening grows rougher, deeper, more connected. By the time many seasons have passed, that once modest joint has become a drainage path. It may connect to another below. It may undercut a small block. It may open to a hidden cavity in the shattered rock behind the face. What began as line becomes passage. And because water follows the easiest path, passage tends to invite more passage. This is a second kind of selection, different from frost but allied with it. Frost tends to activate cracks with good moisture supply and favorable thermal conditions. Dissolution tends to enlarge the pathways that already accept water efficiently. When both processes work together, the mountain's internal architecture becomes more legible. Some seams remain minor, others become organizers of the terrain. This can be seen on the upper pavements where broad, pale slabs are interrupted by straight or wandering fissures. Stand over one and look down. At the top, only a narrow opening. A little lower, the sides flare and darken with moisture. Still lower, the crack is hidden by shadow, damp moss, or trapped leaves blown up from lower slopes. The fissure has become deep enough to hold its own miniature environment. It is no longer just a break in stone. It is a boundary between blocks, a water route, a cold trap, a future line of separation. The limestone surface around it also changes. Where meltwater flows over exposed stone before entering the opening, it can etch shallow runnels. These tiny grooves gather other films of water, guiding them along the same paths. A smooth bed becomes delicately corrugated. In places where water ponds briefly, shallow pans can form. In hollows with enough retained sediment, organic matter accumulates. That organic matter raises carbon dioxide levels in the tiny water films, increasing their dissolving effect. So once again, the process feeds itself. Opening permits retention. Retention changes water chemistry slightly. That chemistry helps deepen the opening. These are small effects, but mountains are patient enough to use small effects well. The consequences spread downward through the massif. A talus apron, leaning against bedrock, is not sealed from the mountain behind it. Meltwater entering through the rubble may reach joints at the bedrock surface. Some of those joints have been widened mechanically by frost. Now they are also enlarged chemically by percolating water. Because limestone beds are layered, and because fractures often connect between them, water can be redirected underground. A seep that once issued openly from a cliff base may weaken as the drainage pathway shifts inward. A damp patch in summer may become a dry one, not because less water arrived, but because the route changed. Elsewhere, a small spring may appear lower on the slope where hidden pathways converge and daylight returns. This is the mountain reorganizing its plumbing. At first, the changes are local. A crack accepts more water than before. A hollow drains unexpectedly fast. A patch of turf remains greener because seepage now emerges beneath it. But taken together, those local changes mark a threshold. The limestone is becoming a breathing terrain, exchanging water between surface and depth. In a high alpine setting, this transformation is never purely chemical or purely mechanical. Cold remains part of the story. So does snow loading, thaw timing, and rubble movement. Yet the new pathways matter so much that the look of the mountainside begins to change. On exposed pavements, grikes widen. On ledges, detached blocks stand farther from the parent rock. At the base of certain cliffs, sink points form where runoff repeatedly vanishes into debris and fractured bedrock. These are not large, dramatic holes. Often they are quiet inlets, half hidden by stones and sedges, but they indicate a new logic. Water that once traveled across the mountain now travels into it. The Alps are full of such transitions in limestone areas. A slope may begin as bare fractured bedrock with talus below. Then, over long time, widened joints and dissolving seams create a pavement broken into blocks. Between those blocks, grikes deepen and collect soil. Elsewhere, runoff finds a sink among fallen stones. Below the surface, enlarged cracks connect to bedding planes and small conduits. The visible landscape of cliffs and scree becomes linked to an invisible landscape of hidden flow, and the hidden landscape changes the visible one in return. Where drainage becomes internal, less water may remain on the surface to feed streams. Where a seam is kept wetter from within, frost action may remain active longer. Where subsurface roots enlarge, support beneath a block can be reduced. All of this contributes to the gradual separation of the mountain into forms. A detached tower rarely owes its existence to one cause. Usually it stands because structure, frost, gravity, and hidden drainage all favored removal around it. A ledge broadens because thin beds are lost below. A notch deepens because water keeps choosing that line. A limestone pavement develops because fractures multiplied and then were widened by both ice and solution. Once you begin looking for this cooperation, it appears everywhere. Take a broad shelf just below the cliff line. At first glance, it seems simply broken and rough, but after snowmelt, little streams move across it in short silver lines, each line ending at a crack. Some cracks are newly pale and sharp-edged, others are dark, widened, and lined with moss. The pale cracks tell of recent mechanical opening. The dark ones tell of sustained moisture and developing internal drainage. Sometimes the two overlap. A recent break provides fresh stone beside an old damp fissure. That is the mountain speaking in two times at once. One time is seasonal, visible in the newest fallen fragments. The other is cumulative, visible in the established water roots that have taken many years to form. As these roots multiply, the very feel of the limestone plateau or ledge changes underfoot. Solid bedrock becomes interrupted by slots and grooves. The safe broadness of a slab becomes broken by regular openings that must be stepped across. Not because the place is dangerous in any dramatic sense, but because the rock has been articulated into separate units. Each clint, each block of pavement stands a little apart from the next. Frost helped define the boundaries. Water deepened them. This is how a mountain that once seemed massive and seamless reveals its inner partition. If you kneel beside one moist fissure in late summer, you can sense the persistence of hidden water. The surface may be dry, the air may be warm for this altitude, yet from the crack rises coolness. Deep within, where sunlight does not reach, water is still moving or resting on stone. That coolness is part of why these openings become important habitats later. But before life takes hold strongly, the geometry itself must widen enough. Some joints remain narrow because the supply of water is limited, some close against one another where the rock mass is still tight. Others open decisively because several favorable conditions coincide. A snow patch lingers above. A bedding plane feeds seepage into the joint. Frost detaches thin sheets from one side. Meltwater, slightly acidic, continues the work. As a result, a crack that was once measured in millimeters becomes measured in fingers, then in hands. Once that happens, a block is no longer merely fractured, it is separated. Not fallen yet, perhaps, but structurally distinct. That distinction matters for the whole mountain profile. When enough fractures reach this stage, walls become buttressed. Buttresses become towers. Towers become isolated forms with chutes between them. The visible grandeur of Alpine limestone often comes from this long partitioning. The scale is large, but the mechanism is intimate. Night water in small cracks, sunlight on one ledge and not another. Snow held in one recess and blown clear from the next. Everything depends on differential exposure and patient repetition. Now the circulation of water through hidden roots begins to affect the lower slopes more clearly. At the toe of a talus fan, where a streamlet once ran openly for several meters, the flow now disappears sooner each year. A few steps downslope, a damp patch appears in turf where no surface runnel connects to it. This suggests an underground short path through rubble and fractured bedrock, not a cavern in the dramatic sense, only a connected seepage system. Yet even such small subterranean diversions alter where finds are deposited, where soils remain moist, and where frost can return in early cold. A patch of saturated ground may freeze hard in autumn and heave slightly. A neighboring patch, better drained, remains more stable. These tiny differences echo upward into ecology. But the geological part comes first. The mountain keeps opening. On some high pavements, Widened grikes create rectilinear patterns that reflect the original joint network in the limestone beds. The blocks between them can look almost arranged by hand, though they are entirely natural. On inclined slabs, runoff etches grooves that lengthen with time, converging toward openings. In hollows at the base of walls, sink points form beneath unstable debris, swallowing melt before it can build a visible stream. In all these places, frost wedging has served as an initiator. It roughened the rock, it detached the edges, it made fresh surfaces vulnerable to dissolution. It increased the total area where water could interact with stone. This is why karst in cold mountains often has a different feel from karst in warm lowlands. The Alpine version is sharper, more angular, more clearly partnered with mechanical breakage. Its pavements are not only dissolved, they are also frost-cut. Its depressions are not only solution hollows, they are often bordered by shattered stone and snow-abraded ledges. Its drainage points are not always smooth funnels. Sometimes they begin as broken seams among blocks. This mixed origin gives the landscape a peculiar clarity. You can see both the fracture and the flow. You can read both winter and water. As the process continues, a new reveal appears on the broad upper surfaces. Some depressions keep snow longer because they are deepened enough to shelter it from wind and sun. That lingering snow delays warming, feeds seepage later into summer, and maintains moisture where surrounding rock has dried. In turn, the moist margins of those depressions experience more freeze-thaw stress during shoulder seasons. The depression therefore deepens further, not only by dissolution but also by frost prying along its edges. A small hollow becomes more definite each decade. A cluster of hollows develops on a pavement where joints and surface runoff intersect. The mountain is learning to hold water in some places and lose it quickly in others. That selective retention becomes part of its surface pattern. Below the pavements, hidden channels in the shattered limestone carry cold melt through darkness. Most are tiny. Some are only widened joints with intermittent trickles. But given enough time and enough connected pathways, larger conduits can begin to develop. At this stage in the story, it is enough to recognize the direction of change. The massif is no longer being shaped only from the outside in. Water has entered. It is helping shape the stone from within. This is the irreversible turning point in the landscape logic. From here, the stone above and the hidden water below begin to affect the quieter parts of the slope in ways that are easy to overlook. A shallow crack that once held only melt for an hour can now hold dust, then moisture, then the first trace of dark mineral stain. That stain is a small reveal because it marks a place where water returns often enough to leave a memory. On exposed ledges, the pale limestone remains hard and bright, but in protected seams, the color shifts. Gray-green films of lichen spread first, then a little moss in the coolest shadows, then, in a pocket no wider than a hand, a thin line of soil that was not there a few seasons earlier. None of this would matter much if the rock was still sealed, but the cracks are open now. They are wide enough to keep what wind brings. They are deep enough to hold last night's dampness after the surface has dried. And that changes the mountain once again. A ledge that used to shed everything now begins to retain. Dust blown up from the cirque floor catches behind small ribs of stone. Pollen settles there. Fragments of dried grass lifted by wind from lower meadows lodge in narrow corners. Tiny flakes of limestone from the cliff itself crumble into the same places. Over time, these materials mix into a fragile skin. Not true deep soil, only a dark, thin beginning. But in alpine country, a beginning is enough. Seeds arrive almost invisibly. Some come on the wind, some are carried in mud on the feet of birds, some simply tumble from a plant growing higher on the slope. Most will not take hold. The ledge is too dry, or too cold, or too unstable. Yet a few meet exactly the right conditions. A little shade, a little moisture, a crack that reaches deeper than the eye can see. There, life enters the mountain by the same routes water used first. The earliest settlers are often the smallest and quietest. Lichens spread across the limestone in pale circles and map like crusts. They do not look like much from a distance. Up close, they soften the brightness of fresh rock with powdery silver, yellow-green, and muted ash. They can survive where almost nothing else can. They cling to exposed faces, absorb moisture from rain and mist, and wade through cold. In doing so, they begin to alter the surface very slightly, not by force, by contact, by staying. Moss follows where moisture lasts longer. A shaded seam below a lingering snow patch becomes dark with it. The stone there remains cool, even under summer sun. Water trickles through after thaw and disappears beneath a tuft of green so small you might miss it entirely. That tuft is another kind of evidence. It tells you the crack is not only open but dependable. Moisture returns here often enough for life to trust it. Then come the plants that belong to high limestone places. A saxifrage rooting in a narrow cleft. A cushion plant pressed low against the wind. A tufted grass at the outer edge of a ledge where fines have gathered. These are not lush arrivals. They do not cover the cliff. They appear one by one, like thoughts settling into a quiet mind, yet each one changes the stone around it. Roots are patient tools. They do not strike. They enter where frost has already prepared a way. A hair-thin root follows a damp line into the rock. As it grows, it anchors particles, traps more sediment, and holds moisture a little longer after rain. That retained moisture matters. A dry crack may do little in an ordinary cold night. A damp one remains active, so the plant does not replace frost wedging. It joins it. The consequence is gentle, but cumulative. A crack that once opened only in winter now stays biologically occupied through summer. Its edges remain cooler. Its interior holds organic matter. Its chemistry changes slightly because decaying plant material enriches the water with more dissolved carbon. That makes the water a little more effective at dissolving limestone. Again, the mountain shifts by cooperation. Frost opens, water enters, life settles. Then, life helps water stay. On broad limestone pavements, this pattern becomes easier to read. The clints, the standing blocks of bedrock between the fissures, remain bare on their upper surfaces. But inside the grikes, those deep splits between blocks, the world turns darker and softer. Soil gathers there first, not much, only enough to support narrow roots and a few protected stems. The top of the pavement may look austere and bright, almost severe in strong mountain light. Yet between the stones, hidden from the sun, there is a miniature garden, tiny ferns in the deeper shade, mosses where drip persists, low herbs, and seedlings reaching upward from cool, sheltered slots. This is one of the most beautiful results of frost-shaped karst. The rock becomes a framework for quiet life, and because the grikes are aligned with fractures, the plant pattern is not random. It follows geology exactly. Where joints are wide, soil collects deeply. Where a crack narrows, roots thread downward in tight lines. Where blocks have separated just enough to create a pocket at their meeting point, a cushion plant may spread there, round and dense, holding heat and moisture close to itself. Seen from above, the pavement becomes a map of living response to broken stone. The same thing happens on scree margins, though differently. Upper talus remains too mobile for most rooted plants. Every winter shifts it. Every thaw redistributes support. But the edges of the scree begin to stabilize sooner. There, between larger blocks, fine material gathers. A stone shelters wind-blown dust. Meltwater slows behind an obstruction and drops silt. A little organic matter darkens the pocket. Then a first pioneer takes root. The roots bind the fines. The bound fines hold more moisture. The moisture encourages more plant growth. Little by little, the margin thickens. What was once an abrupt border between rubble and meadow becomes a gradation. Bare, angular stone. Then lichen-darkened blocks. Then moss in the shaded recesses. Then sparse plants. Then a more continuous thin turf beyond. This transition is not decoration. It records the slowing of movement. Where plants can settle, the ground has quieted enough to allow them. Where the scree still runs with each thaw, the stone remains mostly bare. So vegetation becomes another way to read process. A green patch beneath a cliff often means one of two things. Either little fresh rock is arriving there, or enough fine material and moisture are being retained to outpace the disturbance. Sometimes both are true. At the foot of one broad limestone wall, you might find three neighboring zones telling three different versions of the same story. Directly below, an active chute. Blocks lie bright and unstable. To one side, a partly sheltered apron supports scattered saxifrages and grasses among old stones. Farther out, where the fan has thinned and calmed, a fuller meadow begins. All three zones share the same source cliff, but the intensity of frost delivery and the pattern of water movement differ. That is the mountain's decision, though not a conscious one. It decides by structure, exposure, and slope where stone will keep moving and where stillness can gather. Ledges high above show the same sorting. A narrow shelf beneath an overhang may remain almost bare because fragments continue to fall across it. Another shelf only a few meters away, protected from direct rockfall and fed by a dependable seep, becomes a hanging strip of moss and low flowers. The difference can be startling when seen up close. One side all chalk white fracture and sharp debris, the other edged in muted green, with roots entering the same kinds of cracks that frost once widened. The science remains simple, even here among the plants. Roots exert pressure as they grow. Not enormous pressure all at once, but enough over time to exploit existing weaknesses. More important still, plant cover changes the water balance. It slows runoff, it shades stone, it traps snow in some settings and retains dampness in others. So where a bare crack might dry quickly after a storm, a rooted crack may stay moist longer. That longer wet period increases the chance of freeze-thaw action when temperatures hover around freezing. In high alpine limestone, these overlaps matter far more than any single mechanism alone. A plant does not split a cliff by itself. A frost night does not create a meadow by itself. But together, over many seasons, they organize surfaces into habitats. Consider a small cushion plant on a sunny limestone ledge. Its leaves are packed tightly into a dome no higher than your hand. Inside that dome, air is calmer and moisture is conserved. At its base, fine particles accumulate. The plant's roots enter a network of microscopic and hairline fractures in the limestone beneath. Water from rain or melting snow lingers around those roots. Then, in autumn or spring, cold returns. Ice forms where moisture has been held. The rock around the root zone may loosen further, grain by grain. Meanwhile, dissolved limestone carried by seepage leaves tiny changes in the crack walls. The plant remains where it is because the ledge exists. The ledge changes because the plant remains. That reciprocity is one of the quiet themes of this mountainside. Even lichens, which seem almost motionless in time, contribute to the softening of form. They trap dust. They produce weak organic acids at the rock surface. They create rough microtextures that hold a little more water than polished bare stonewood. A fresh fracture face gleams almost white. A weathered one, long inhabited by lichen and seasonal damp, turns muted and complex. Color begins to separate the young rock from the older. Freshness is bright, persistence is darkened. Life gathers on what has lasted long enough. This is why a limestone massif can be read in patches of tone as well as in the geometry of fractures. Now the mountainside has become richer than a simple contrast between cliff and scree. There are cliff bands still actively breaking. There are talus tongues still moving. There are karst pavements swallowing meltwater. There are ledges collecting soil. There are seep lines marked by moss. There are quiet shelves where tiny plants have established a hold. Every one of those places traces back to frost opening the rock. Without the widening of cracks, there would be fewer pockets. Without the pockets, less water would stay. Without stored moisture and fines, most alpine plants would find no foothold on the pale stone. So the same process that removes matter from the mountain also creates places within it. That is an important reveal in the landscape. Erosion is not only subtraction, it is also arrangement. Some habitats are especially tied to prolonged snow. Below a recess where drifts gather each winter, the limestone stays damp well into summer. There, the rock surface may be darkened by algae and moss, and a fringe of delicate flowering plants appears after snowmelt. These snowbed communities exist because the mountain stores winter in certain shapes, and those shapes often owe their existence, at least in part, to repeated frost breakage. A niche widened by old detachments catches more drift. More drift means later melt. Later melt means longer moisture retention. Longer retention favors certain species and prolongs weathering along the niche edge. The geometry of the cliff feeds the timing of life. Look along a broken ridge path where walkers sometimes pass in late summer. Underfoot, the limestone alternates between bare, pale slabs and narrow, soil-filled seams. Those seams are the mountain's opened lines. They are where roots gather, where insects disappear from sight, where lingering damp keeps the ground cooler than the surrounding rock. The pattern can run for many meters, each line reflecting a joint widened first by frost, then by water, then occupied by life. The ridge may feel exposed and skeletal in the broad view. At the smaller scale, it is intricately furnished. On lower rubble fans, the relationship between plants and stone can become even more layered. A large block fallen long ago provides shade on its north side. Snow lasts there a little longer. Moss thickens in the cool pocket behind it. As the block slowly settles, finer particles accumulate at its base. A grass tuft roots in that miniature terrace. The grass traps more wind-blown material. The terrace deepens. Meanwhile, the block itself begins to split along a seam. Water enters, winter cold returns. A new thin plate peels away from its upper face. The block is weathering, while simultaneously becoming a nursery for life. This is not an exception. It is one of the common destinies of old limestone debris. That is why ancient talus fans often look softened at the margins without losing their underlying structure. The stone remains angular, but it has been threaded with roots and darkened by time. The fan records both fracture and settlement. The ecological response also depends strongly on aspect. A south-facing limestone slope receives more sun. It dries faster. Plants there tend to occupy deeper cracks, more sheltered pockets, and the margins where fines gather sufficiently. A north-facing slope holds moisture longer, keeps snow later, and supports mosses and cold-loving species in thinner openings. So even within one massif, frost-made spaces are used differently depending on direction. Again, the same mountain holds many small climates. That matters because frost wedging itself is aspect sensitive. The biological use of its results is just as sensitive. A dry, sunny ledge may preserve a crack as bare pale stone for years, widening only slowly. A shaded, moist cleft nearby may darken, deepen, root, and soften into a miniature ecosystem much sooner. Neither is more natural than the other. They are simply different outcomes of the same opening process. It helps to slow down and notice how little is required for this transition. A seam wide enough to fit a fingertip can hold enough dust for a moss line. A pocket no deeper than a thumb joint can retain enough moisture for a saxifrage seedling. A block resting against two others can create a shaded void where snow survives late and cold lingers. In high mountains, abundance often begins in scarcity. The first life does not need broad soil, it needs persistence. And persistence in limestone country is often written into cracks. With time, these scattered footholds become patterns visible across whole slopes. Bright bare walls correspond to zones of active breakage. Below them, fresh scree remains mostly open. At the more stable edges, green begins. Higher pavements show dark lines where grikes support plants. Lower terraces beneath spring seeps become soft with moss and herb cover. Even the roots of animals, quiet and occasional, tend to follow these transitions because footing, moisture, and forage differ there. But the mountain remains the central subject. The life is not a separate story. It is a continuation of the geology. One season illustrates this clearly. After a spring with prolonged snowmelt, the moisture retained in cracks is unusually high. Summer arrives, and the plants on ledges look fuller than usual. Moss darkens the fissures, grasses along stabilized scree margins seed heavily. More organic matter enters the system that year. Then autumn brings alternating wet days and freezing nights. The cracks occupied by roots and litter stay damp longer than bare surfaces. They freeze repeatedly. Small flakes loosen from ledge fronts. A shallow seam opens further around a rooted plant. A fallen block on the fan splits across a moss-lined joint. By the following spring, several fresh fractures coincide with the places that held the most life. This is not because the plants are attacking the mountain. It is because they helped create favorable moisture conditions for frost. The consequence is subtle, but real. Habitats deepen the very spaces they occupy. Now imagine the massif from a little farther away. You are no longer focused on one crack, one block, or one tuft of moss. Instead, the whole limestone body rises in steps and walls, cut by couloirs, crossed by ledges, pale under morning light. From this distance, what looks grand and sculptural is really the accumulation of tiny repeated events. A pinnacled ridge is the long outcome of many separated blocks. A wide pass between limestone shoulders is the enlarged expression of multiple lines of weakness opened and cleared over time. A debris apron at the foot of a tower is the visible history of stone leaving one particular set of fractures. Scale begins to change the feeling of the story. At close range, frost wedging seemed intimate, water entering a seam, ice growing in darkness, a chip loosening. At massive scale, the same process becomes architectural. Ridges sharpen, buttresses stand out, towers detach in stages from parent walls, passes lower slightly as frost and gravity remove material from structurally favored lines. The mountain looks monumental, but its monumentality has been assembled from innumerable winters. This is where alpine light becomes part of the reading. Pale limestone carries light differently from darker rock. At dawn, ridges glow cool and silver. By late afternoon, they warm toward cream and faint gold. As shadows lengthen, every recess deepens in tone. Couloirs become blue-gray ribbons between illuminated buttresses. Talus fans fade from bright chalk to muted ash. This shifting light does more than create beauty. It helps reveal structure. Cracks show as dark lines. Detached blocks cast narrow shadows. Ledges step out from walls. The massif becomes legible because light reads the fractures for you. Stand in an alpine basin at dusk, and the whole limestone wall can seem to sharpen as the sun lowers. Not physically, of course, but visually, yes. The oblique light catches protrusions and leaves the clefts in cool shadow. A tower separated from the wall by only a narrow groove suddenly appears distinct. A broken ridgeline resolves into individual blocks and pinnacles. A pass between two walls shows itself as the product of repeated removal, not merely as empty space. The mountain's form becomes easier to understand when the light is low. That form tells the long story of frost more clearly than any single rockfall ever could. Take one limestone tower standing above a scree basin. From below, it feels singular, almost self-contained. Yet if you follow its edges, you see the clues of how it came to be. Vertical joints isolate it on either side. A bedding surface helps define a ledge halfway up. At its base, the talus apron is broad, bright, and continuously supplied. The tower exists because adjacent rock was easier to remove. Frost wedging helped make that difference visible. Year after year, water entered the side cracks. Freeze-thaw cycles widened them. Detached blocks fell from the margins. The groove between tower and wall deepened. Eventually, what once was part of a broader face stood apart as a distinct form. This is true across entire limestone massifs. The famous sharpness of high alpine karst landscapes, the serrated skylines, the pale pinnacles, the buttressed cliffs, all emerge from repeated selective opening along structure. Not all by frost alone, of course. Glacial carving, uplift, and dissolution all matter. But in exposed high limestone, frost wedging remains one of the patient sculptors that gives edges their clarity. The large slopes below those towers carry the same signal. Some are smooth enough from afar to look almost poured into place, yet once you approach them, their roughness becomes apparent. Angular blocks, open spaces, narrow channels where smaller stones have traveled farther. The basin echoes differently there too. Sound in a limestone cirque often feels hard and clean. A loose stone striking others sends a dry rattle that moves down the slope in steps. Even silence seems crisp among pale walls. This acoustic quality belongs to fractured landscapes. They are full of surfaces and voids. Even when still, they suggest the countless small rearrangements that built them. Seasonal repetition remains the hidden rhythm behind the grandeur. In winter, snow fills the higher notches and drapes over ledges, but wind strips exposed ribs. Cold settles into fractures. In spring, thaw opens the first seep lines and darkens the active joints. Summer reveals pale, fresh scars and the geometry of the walls. Autumn rewets the massif and prepares a new cycle of freezing. No one season is enough to shape a ridge, but each contributes a phase. The ridge is the memory of their recurrence. What matters most, across all that repetition, is where the stone yields a little faster than the stone beside it. A notch on a skyline is rarely just a notch. It is often a line of weakness that accepted water more willingly, then cold more often, and then lost more completely. Over centuries, those lines become the passes people notice from far valleys, the pale saddles between higher walls, the angular gateways where one basin opens into another. From close up, a pass may seem broad enough to ignore its making. Its floor is rubble, its sides are stepped with fractured beds, small turf patches gather in the lee of blocks. Nothing in it speaks of sudden removal. Yet if you look at the bordering rock, the evidence remains. Beds are cut by joints that continue across the shoulders on both sides. Detached slabs lie just below fresh faces. Thin seams disappear into shadow where water still enters. The opening between the two ridges is simply where the mountain has been more easily persuaded to part. This is one of the quiet reveals of Alpine limestone. The large forms do not stand apart from the small process. They are the same story, only prolonged. A fretted crest with pinnacles and slots is what many tiny winter actions look like after enough time has passed. A buttress standing clean against evening light is what remains after neighboring fractures became more effective paths for water and ice. The massif is not carved in broad abstract strokes alone. It is divided along actual lines, real seams, inherited planes that cold keeps testing. Once you begin to notice that, even the brightest mountain evening feels full of hidden mechanics. The limestone catches low sunlight and glows softly, but in every dark slit the memory of moisture remains. Snow patches resting in the high recesses are not decoration, they are water held in reserve. When they melt, they do not spread evenly. They choose the old entries. They darken certain joints first. They disappear where the mountain is already open, so the shape of a ridge at dusk is also the shape of future seepage. And future seepage means future winter work. The beauty and the process are inseparable. Down below, where the walls release their long shadows into the basin, the scree begins to cool before the meadow does. That timing matters. Loose stone loses warmth quickly. Open voids let cold settle within. A talus apron can become thermally different from the grassland beside it within the same hour. By night, one patch of ground may still release the day slowly. Another, only a few steps away, may already feel like stored winter. This difference becomes part of the mountain's larger organization. Stone rivers stay cold. Meadow margins gather moisture. The contact between them becomes a line of transition that can persist for generations. You can see it in summer if you sit long enough near the base of a limestone tower. The freshest debris lies pale and open, almost bare of life. A little farther out, the larger blocks are still angular, but their upper faces hold lichen. Farther still, between older stones, sedges and grasses have threaded roots into fine, dark sediment. At the quietest edge, the rubble all but disappears under alpine turf, though the ground beneath still remembers its stony origin. This graded change is not random recovery. It is the visible consequence of declining movement. Where rock is still arriving, plants wait or settle only in small pockets. Where delivery has slowed, roots gain time. Where roots gain time, moisture stays a little longer. Where moisture stays, frost has more to work with during the shoulder seasons. So even the stiller edge of the fan remains tied to the same patient engine above. Now the massif can be read as a set of linked zones. High walls where separation begins. Narrow chutes where fragments are guided downward. Talus aprons where gravity sorts what frost has freed. Pavements and ledges where water disappears into openings. Margins where stillness accumulates enough for soil. And beyond those margins, quieter ground where the mountain's losses have become the substance of future growth. None of these zones is final. Each shades into the next. Each can change pace with aspect, snow cover, and the structure of the rock beneath. A ledge that seemed stable for decades may begin to feed debris after one old crack finally links with another. A green margin may be reset by a fresh spill of blocks from above. A seep that nourished moss one summer may vanish the next as water shifts into a deeper root. This uncertainty gives the limestone landscape its sense of being both ancient and active. It rests, but it does not stop. If you walk higher toward one of the pale passes near evening, the footing itself becomes a lesson. On the broader slabs, the soles meet smooth weathered limestone with only a little grit. Then the surface breaks into angular fragments. Then a shallow groove appears, worn by runoff and edged with frost-loosened chips. Then a seam opens and continues ahead for several paces, dark with retained dust. Each change in texture reflects a different balance between intact rock, fresh fracture, and accumulated material. The pass floor becomes a place where many stages coexist. Some blocks there may have fallen in the last few winters, others have rested long enough to soften at the corners. The whole opening is an archive of transit, and because passes receive wind from both sides, snow often gathers there in complicated patterns. Drifts form behind step-like beds. Wind strips exposed knolls bare. The result is unequal moisture supply in spring, which means unequal frost activity in autumn, and so the pass keeps refining its own shape. In broad daylight, this can seem almost too quiet to notice. But under changing weather, it becomes easier to read. A misty morning leaves the active seams darker than surrounding stone. A late patch of snow marks a shallow depression where cold and drift have lingered together. After rain, the first places to dry are the most exposed ribs. The last are the recessed joints, the little shelves, the grikes, the contact zones between block and bedrock. Drying itself becomes evidence. It shows where water lives longest in the massif. Those are often the same places winter will return to most effectively. This is why the Alps limestone looks so articulated under ordinary conditions. Not because each ridge is especially dramatic in a single instant, but because the mountain has had a long time to separate itself along useful lines. Pinnacles do not require violent events to become distinct. They require enough winters for adjacent rock to be reduced and removed. A broad buttress can remain standing simply because its joints are more widely spaced, or because its geometry sheds water differently, or because less snow lingers in the seams that would open it. Nearby, a thinner rib may come apart more readily. The contrast appears grand. The causes remain intimate. By now, the larger pattern of the massif has become clear enough that you can look from one feature to the next and feel the same logic repeating. A tower over a scree fan. A couloir beneath a snow patch. A ledge with dark, vegetated cracks below pale, fresh scars. A pass where fractured beds and rubble make the ground bright and angular. The details vary, but the progression stays familiar. Water enters. Cold acts. Stone loosens. Gravity receives it. Openings deepen. Life settles where motion slows. Then the next season begins again. Yet the mountain never returns to the exact same state. A fragment gone from the wall does not replace itself. A widened joint does not close easily. A new soil pocket does not become blank rock again unless fresh disturbance strips it away. So every cycle contains a small one-way movement. This is the irreversible quality hidden inside the repetition. The process may feel circular from season to season, but the form it creates accumulates direction. The wall becomes more divided. The slope becomes more organized. The drainage becomes more internal. The habitats become more patterned. Nothing is undone simply by the return of summer. As the light fades further, the pale ridges across the basin hold their last brightness long after the floor has gone cool. This kind of alpine evening makes the massif seem suspended. The high rock glows. The talus below is already grey. Between them, the broken ledges and shelves appear as bands of softness and hardness, of retention and release. Even without moving, the whole scene suggests transfer. Stone from above to below, water from surface to crack, fines from crevice to soil, time from one season into the next. And beneath that transfer lies the older memory still present in the rock itself. This limestone began as seafloor, layered sediment in warm, shallow water. Calcium carbonate settling, compacting, hardening into beds. Later, tectonic compression raised and folded those beds high into the Alps. Now cold takes hold of the inherited plains from that ancient origin. The sea left structure, the mountain climate reads it. That connection gives the landscape a peculiar calm. The ridge is bright and sharp, yet its logic reaches back to quiet deposition under vanished water. The basin below is full of broken fragments, yet each fragment is part of an older, layered story. Even the scree fan is composed of ancient marine material now resting under snowmelt and alpine grass. Nothing here is disconnected. The highest pinnacle and the smallest chip on the fan belong to the same long material journey. That is why the ground beneath the cliffs feels different when you stop and look instead of crossing quickly. The pale blocks are not merely debris. They are the present form of the massif's memory. They preserve bedding in their flat faces. They preserve fracture in their edges. They preserve transport in their arrangement. And once they settle, they begin another phase of quiet change. Some where you stand are already half buried in fines. Some sit open and clean as if they landed yesterday. Some support moss on one face and a fresh frost split on another. The slope gathers time scales together. Old fall, recent fall, ongoing fall, stillness and motion living side by side. A basin like this often looks empty from afar, yet it is full of slow decisions. Where a snow patch will last, where a trickle will sink, where a root can enter, where a slab will separate next. These decisions are made by exposure, bedding, joint spacing, elevation, and the ordinary temperature swings of the mountain year. No single force dominates completely. That is why the landscape remains varied. Even neighboring walls can age differently. A thicker bedded face may shed large planar slabs that build a coarse talus apron. A thinner, more fractured face may yield smaller angular rubble and develop deeper grikes on its exposed pavements. One pass broadens into a gently rising saddle, another stays narrow and broken, almost stair-like with detached beds. The massif contains many expressions of the same patient mechanics. By late dusk, the details begin to simplify. Color drains from the stone, edges become silhouettes, the biggest forms remain: ridge, tower, pass, scree cone, cirque wall. This simplification does something useful. It lets you see how much of the mountain's visible character depends on subtraction. The void between two towers is removed stone. The basin beneath a wall is partly built from removed stone. The open crack along the pavement is missing stone. The meadow margin owes its soil, in part, to reduced stone. Frost wedging is not the only agent of that subtraction, but it is one of the most consistent in these cold limestone heights. It works where attention rarely lingers, in dark joints, under snow edges, behind loosened slabs, within rubble voids, yet the forms it helps create dominate the entire view. Now the perspective begins to lower again. From the high ridges and the broad reading of the massif, attention returns to what remains underfoot after so many winters of opening. The descent is gentle. You leave the skyline and follow broken limestone down toward the foot of the wall. The ground grows quieter with each step. Wind that moved freely across the ridge weakens among the blocks. The basin receives the evening cold and holds it. Here, at the base of the cliffs, the process feels less like architecture and more like accumulation. Stone lies where it has come to rest, at least for now. A block the size of a chair leans against another. Thin shards overlap like fallen pages. Small chips have gathered in the narrow hollows between larger pieces. Everything is angular, everything is pale, unless time has muted it. This lower world is less dramatic to the eye, but in some ways more complete. The wall above shows where separation begins. The ground below shows what separation becomes. You can choose almost any single fragment and find a clue to the larger mountain in it. A slab reveals bedding. A wedge records two intersecting fractures. A block with one weathered face and one fresh face shows both age and recent opening. Some pieces are roughened by dissolution along tiny pits and channels. Some have broken cleanly enough to show crystalline sparkle in the limestone matrix. Some are already cracking again where moisture and cold have resumed the work at smaller scale. Nothing has arrived here finished. Even after falling, the stone continues to change. The plane of broken stone, if you can call it a plane, is not flat in the strict sense. It rises and falls gently in small ridges and hollows built by deposition, settling, and partial reworking by snowmelt. Yet compared to the sheer wall above, it feels broad and low, almost level in spirit. That feeling matters. The eye relaxes here. Cliffs demand upward attention. Talus at the base draws the gaze downward, to detail, to texture, to arrangement. And because the basin floor is quieter, the evidence of long duration becomes easier to notice. Some stones have lichen thick enough to soften their outlines. Others are ringed by fine sediments deposited after many seasons of runoff. In places, the rubble is so old and still that turf has begun to bridge between blocks, making a surface that appears stable until you look closer and see the pale fragments just beneath. Elsewhere, a fresher ton of scree crosses the older ground like a brighter stream. This contrast between old and new is one of the most restful ways to understand ongoing weathering. The mountain is not collapsing, it is transferring material at unequal rates. Some patches wait, some patches receive. Some patches are already becoming something else. A broken stone basin in Alpine limestone country often contains all these states in view at once. Near the cliff base, the stones are largest and newest on average. They have not traveled far. A broad slab may still lie almost directly beneath its source bed. A cluster of chips may mark where impact split a recently fallen block. Step outward from that zone, and the fragments tend to become smaller, though never with perfect regularity. Large pieces sometimes bounce farther than expected. Snow can carry or cushion them. Meltwater can undercut finer deposits and make them shift. Still, a general grading persists. Outward means older, finer, more settled. And with greater settling comes the first persistent quiet. That quiet is not silence alone. It is a kind of mechanical calm. Blocks no longer shift each season. Voids are partly filled. Fine sediment stays in place long enough to darken. Roots remain through winters. A place begins to remember stillness. This is an important consequence of the whole process. Frost wedging does not produce only fresh scars and falling fragments. It also produces surfaces that, after enough transfer and enough waiting, become the groundwork for stability. The plane of broken stone is therefore both aftermath and beginning. It receives the mountain's losses, then slowly redistributes them into patterns of rest. In one hollow near the toe of the fan, for instance, limestone chips smaller than a thumb have accumulated with dark silt and bits of organic matter. A trickle after snowmelt probably laid some of it there. Wind may have contributed more. The hollow stays moist longer than the surrounding rubble, because its fine material holds water. That retained moisture supports a thin carpet of moss. The moss, in turn, traps more particles. The next year, the patch will likely be slightly deeper, slightly darker, slightly more cohesive. No sudden transformation occurs, only a small increase in staying power. A few steps away, a larger block lies with one end slightly raised on buried rubble and the other settled into damp ground. Its upper face remains mostly bare. Its shaded lower edge is lined with lichen. Underneath, protected from sun and direct rain, the ground is cool and dark. A tiny arch of space remains there. Snowmelt enters. Cold air lingers. If you looked in early spring, you might find a remnant of ice preserved longer than on nearby open ground. That preserved cold can matter for frost activity around the contact points between block and sediment. Even the resting stones continue to create microclimates. This is why the basin floor is never geologically inactive, even when it appears still. The mountain's broken surface is full of small thermal differences. A block shades one patch, a void channels air through another. Fine sediment holds dampness here, while coarse open rubble dries quickly there. These variations influence whether frost can work, whether water can sink, whether roots can remain. The larger process is now spread among thousands of little conditions. Stand in the middle of the old scree and look back up. The cliff is high, but it no longer dominates completely. The ground around you has enough character of its own. Pale, angular fields stretch outward. Older deposits blend into meadow edges. A narrow line of fresher stone descends from a couloir and ends against older rubble. Small sink points, half hidden by grass and fragments, take water underground. Here and there, limestone pavement emerges where finer cover is thin. The whole lower slope becomes a mosaic produced by repeated supply from above and selective quiet below. That mosaic is what long winters leave behind when they are allowed to work patiently. It is also where the mountain's history becomes touchable. You can rest a hand on a slab and feel the fine roughness left by weathering. You can trace a bedding plane with your fingers. You can see where a crack begins at one edge and fades into the center, not yet fully opened. You can notice the powder of fresh limestone at the base of a smaller split. Every fragment contains the same logic in miniature. Water once entered, cold acted, a line weakened, stone yielded, then gravity carried the result to where you are standing. Because this is limestone, another layer of time remains visible too. Many fragments preserve textures from deposition that far predate the mountain itself. Some show tiny fossil traces, some reveal subtle grain differences between beds. A flatter slab may carry faint laminations, the memory of quiet marine settling. A rougher piece may reflect shell-rich material or reef debris compacted long ago. These details give the plain of broken stone an almost impossible depth of history. Ancient seafloor, lifted into mountain walls, then fractured by alpine frost, now resting among moss and sedge, beneath a cold evening sky. The process feels slow because it is slow, but it is not empty of movement. Night after night, winter after winter, the transfer continues. And because the transfer is ongoing, the lower basin never becomes entirely finished. One old fan may be cut by a newer tongue of debris. One stable patch may begin to move again if its source wall above becomes newly active. A sink point may capture more runoff after a fracture opens up slope. A damp meadow edge may slowly dry if drainage shifts deeper into the rubble. All of these are subtle changes, yet together they keep the plain responsive. This responsiveness can be read after storms. A heavy summer rain does not produce some dramatic torrent here, but it may wash fine limestone flour from fresh break surfaces into lower hollows. It may darken old joints and show which blocks still admit water. It may make tiny temporary rills across the finer toe of the fan. By the next dry day, most of those traces fade. Still, a little more sediment remains where the water slowed. A little less support remains beneath a precariously balanced chip. A slightly larger stain marks the damp seam under a lichen patch. Accumulation and rearrangement proceed with remarkable modesty. Even snowmelt, which is one of the great seasonal organizers of the basin, usually leaves only understated evidence. Water emerges from under late drifts and disappears into open rubble. Where the flow returns lower down, the signs are gentle but specific. A strip of sedge stays greener than the ground around it, even after several dry days. A shallow patch of darkened gravel marks where hidden seepage reached the surface, then sank again. In places, the limestone chips are faintly rimed with pale mineral crust, left behind as water evaporated from the open air. That is one of the quiet decisions of this lower basin. Some water is guided inward and kept in darkness. Some returns briefly to daylight, touches the broken stone, and leaves a small trace of what it carried. Because the rock is limestone, that trace can be calcium carbonate settling out again in delicate films. The mountain gives material away, then receives a little of it back in another form. You can follow this exchange best in the old deposits, where movement has slowed enough for finer detail to remain. A stable patch of rubble may show a thin skin of silt between angular fragments. A moss cushion darkens one hollow, holding moisture where bare stone nearby dries white and clean. A tiny runnel, active only during melt, has arranged chips into a faint crescent below a block that interrupts the flow. None of these marks lasts unchanged forever, but each is evidence that the basin floor is not simply waste ground. It is a working surface. The consequence of all this slow activity is visible in the way the lower slope begins to separate into textures. Some parts stay open and stony because fresh material still arrives from above. Some parts become patchy with low vegetation because enough fines and moisture now remain through the season. Some parts grow almost smooth with turf, though beneath the grass is still a layer of broken limestone, resting where older winters placed it. This is how the plain of fragments becomes more than a deposit. It becomes terrain. A person crossing it without hurry would feel these differences through the feet before naming them with the eyes. Loose, ringing chips under one step, a firmer crust of fine rubble under the next. Then a tufted patch, springy with rooted sediment gathered between buried stones. The mountain's long transfer from wall to slope has produced a ground that remembers many rates of motion at once. It also remembers the old sea. That sounds improbable in the evening cold beneath an alpine cliff. Yet, it is present everywhere here. A broken slab may show shell-rich texture on one face. Another may preserve a finer-grained layer, laid down long ago in quieter water. The flatness of a bedding plane, now tilted high in the mountains, still records deposition before uplift ever began. So even at the foot of the scree, among the most ordinary-looking fragments, the stone carries an older origin than the ridge above it suggests. This gives the basin an unusual depth of time. Recent frost split the block. Gravity moved it. Snowmelt shifted the chips around it, but the material itself began far earlier, in warm marine settings now vanished. The Alps limestone is never only alpine, it is alpine seafloor raised into weather, and that deep memory continues to influence the present process. Beds formed in layers, and those layers still govern how slabs detach. Joints open during uplift, and those joints still guide water downward. Mechanical weathering in winter is, in a sense, reading a script written when the limestone first became rock. That is why the lower basin feels so coherent, even when its surface seems scattered. The fragments are many, but their shapes are not random. The wider, flatter pieces came from bedding surfaces. The more wedge-like blocks record intersecting fractures. Chips concentrated in one strip likely passed through a chute above, while larger, squarer masses stopped sooner on rougher ground. Each deposit keeps the structure of the cliff in translation. And when enough translations lie together, the whole basin can be read backward, from plain to fan to chute to wall. As evening settles further, the temperature drops through the still air near the ground. The big walls are dim now, their outlines softened, but the rubble at your feet remains sharply present. This is where the story becomes even quieter. The larger forms have already been explained by many winters. Now the attention lingers on what those winters leave behind night after night. A narrow seam in one old block still accepts water after rain. A tiny fracture across another catches enough melt to freeze in autumn. A little pocket of dark sediment supports roots that enter a stone fallen perhaps decades ago. The process has no final finished state at this scale. A fallen block does not retire from weathering, it only changes location. That is important for the mountain as a whole. The cliff loses stone, but the lost stone continues to break, settle, dissolve, and help build future soil. In time, a piece of wall becomes a block, then a slab, then chips, then grit, then mineral-rich sediment in a damp hollow, then part of a turf edge or a thin alpine soil. This is not a neat sequence everywhere, and it does not happen evenly. Still, the direction of transfer remains, from face to slope, from slope to finer ground, from coarse fracture to quiet accumulation. Because the changes are so gradual, the basin never seems busy, and yet it never truly stops. A cold snap after autumn rain may split several small blocks on the old fan. A spring thaw may send a narrow thread of fresh debris across an older vegetated margin. A summer storm may wash finds into a sink among the stones and leave the surface looking almost the same, though its internal pathways have shifted. The reveal is always a little later than the cause. You notice the greener patch after the drainage has already changed. You notice the fresh slab after many unseen freezing cycles prepared it. You notice the subtle sag in the scree edge after support has been reorganized below. That delayed evidence suits the mountain. Everything here favors patience over spectacle. If you stay long enough in one part of the basin, another pattern appears. Old deposits are often smoother in outline than fresh ones. Not smooth like polished ground, but smoother in a geomorphic sense. Their ridges are lower, their hollows hold more fine material. Their block edges are less severe because corner after corner has weathered away. Fresh scree stands bright and angular, ancient scree relaxes. That relaxation is one of the best ways to see long duration in the landscape. A younger tongue of debris cuts down from the wall with a crisp form, pale and open. Beside it, an older deposit broadens into gentler undulations, part rubble, part incipient soil, part meadow edge. The two belong to different moments in the same process. One is active supply, the other is stored history. In limestone country, that history often includes hidden drainage. An older fan may have enough fine filling and enough stable contact with bedrock beneath to direct water into persistent subsurface roots. That means the old fan does not only sit there, it participates in the mountain's internal circulation. Rain and snowmelt enter through loose upper layers, move into zones of older settled rubble, and pass into widened joints below. Some of the water may return as seepage farther out. Some may continue underground for much longer. This is how a pile of fragments becomes part of the Karst system without ever needing to look like a cave entrance. Its openness to water is enough. Its contact with fractured limestone is enough. The lower slope, then, is not the end of the process but a hinge between visible and hidden change. Above, you can see the wall and the fresh breaks. Below, you can feel the moisture in the turf and notice where springs appear. Between them lies the broken apron, accepting stone from one side and handing water to the other. This hinge is why the base of a limestone cliff often seems more complex the longer you look. What first appears to be only debris is also storage, filtration, insulation, and sorting ground. It stores winter cold between blocks. It filters water downward. It insulates little pockets where snow survives late. It sorts material by size and motion, season after season. Every one of those functions matters to frost wedging, even though the most obvious splitting happened higher up. And if the mountain can be said to have a lower body, this is it. The upper wall is all exposure and separation. The lower body is reception and rearrangement. The wall opens, the basin settles what has opened. The relationship is one way in material terms. Stone that has reached the fan does not rise back into the cliff. That one-way transfer gives the story its deeper sense of consequence. Even when the same seasonal cycle repeats, the mountain itself is not returned to its earlier condition. A gap in the wall remains a gap, a fallen slab remains below. A widened grike remains available to next year's melt. A patch of fine sediment trapped among old rubble remains a place where roots can try again. So repetition in the Alps limestone is never simple repetition. It is repetition with memory. The mountain keeps the effects of what has already happened. This becomes easier to feel at the quietest hour, when the basin floor is nearly without sound. No stream is strong enough here to dominate the air. No recent fall interrupts the calm. Only the still arrangement of pale stones under a dimming sky, and in that stillness, the asymmetry of the process becomes almost soothing. The wall above is slowly giving itself away. The ground below is slowly receiving and transforming what arrives. Nothing rushes, nothing resolves completely. The limestone massif remains itself by changing in this steady direction. Not all the lower basin is equally old, of course. One fresh ribbon of debris may cross the older broken ground and stop against a turf edge like a spill of chalk. That ribbon is evidence of a more recent phase of opening above. Perhaps a block boundary finally linked through after many winters. Perhaps a snow-filled recess fed repeated seepage into one small section of wall. Perhaps dissolution along a hidden joint weakened support enough for a slab to let go. The exact sequence may be invisible now, but the result lies plainly among the older stones. That is another reveal of the plane of broken stone. It can record separate episodes without drama. A fresher tongue brightens the darker old rubble. A cluster of large new blocks interrupts a smoother old surface. A new sink point forms where material landed and shifted the route of meltwater. The landscape accepts additions the way a quiet pond accepts falling leaves, by making room, then slowly incorporating them. Even where the plain seems settled, the mountain's ancient structure persists. Walk across an old fan and you may notice long, flat stones lying in repeated orientations. They did not land there by chance alone. Their bedding planes and fracture faces influence how they settle. Some align with the fall line of the slope, some overlap like shingles. Some bridge small voids below. Over time, those positions determine where fines collect, where moisture is retained, and where later frost can act. A stone lying broad and low may trap sediment along its uphill edge. A block raised on corners may create a cold, shaded cavity beneath. The geometry of the fragments continues to matter long after arrival. This is one reason the Alps limestone rarely produces a lower slope that is merely soft and blurred. Even in age, it retains articulation. There are edges, planes, little terraces, miniature ledges, and open slots. The source wall has imprinted itself on the debris field. That imprint slowly weakens, but it does not disappear quickly. And because limestone is pale, these forms remain visible in subtle light. Moonrise on an old scree edge can make flat slabs and angular ridges stand out almost as clearly as low sunlight does by day. Pale rock carries shape into the night. That nocturnal clarity matches the quiet persistence of the process itself. Cold nights matter here as much as bright days. Moisture held under a block, in a seam or inside old settled rubble can freeze without witness. A tiny movement may occur. A crack may lengthen by less than a finger's width. A chip may be prepared to fall next thaw. Eye morning, the basin looks much the same, but the mountain has changed in ways too small for an impatient glance. This is why old talus is never truly inactive. It is simply less obvious. Its movements are mostly internal now. Its role in the massif is mostly distributive. It receives weather from above, holds some of it, passes some inward, softens some into future ground. That future ground begins wherever the rubble quiets enough for continuity. A few adjacent pockets of fines link together. Roots bind them. The next rain does not wash everything away. A thin strip of turf develops between blocks. Then another. The stone is still there, dominant underneath, but the surface behavior has altered. Water now slows at the roots. Organic matter accumulates. CO2 in the damp microsoil rises a little. making seepage slightly more able to dissolve carbonate. Winter freezing returns to a setting changed by biology. The consequence is not that the mountain stops eroding, it is that erosion and habitability become more tightly woven together. In this way, the plane of broken stone extends the earlier chapters rather than merely receiving them. The cliff taught you that the rock was full of weakness. The winter cycle showed how cold exploited those weaknesses. The talus apron showed how gravity sorted the results. Karst openings revealed that water learned to move into the mountain. The ledges and fissures showed life entering the spaces made by frost. Now the basin floor gathers all of those threads in one place. Here are the fragments produced by winter pressure. Here is the hidden drainage encouraged by limestone structure. Here are the first soils formed from broken rock and trapped dust. Here are the old marine beds, visible in fallen slabs. Here is the uneven transition from active movement to rooted stillness. Nothing has been left behind. Everything is lying together under the wall. The more closely you observe the old fan margins, the more this gathered history becomes plain. A limestone chip half buried in turf shows only one sharp corner above the grass. Beneath it may be a larger buried fragment, and beneath that, a deeper body of rubble from many winters before. The meadow edge is often a thin cover over accumulated breakage. Its calm surface is made possible by what has already fallen. That means the quietest part of the basin is not separate from the cliff at all. It is one of the cliff's later forms. This may be the gentlest consequence of frost wedging in Alpine limestone. Not only the making of towers, ridges, and scree, but the preparation of ground where stillness can collect. Even a narrow alpine lawn beside a broken fan may owe its existence to long transfers of mineral matter from the wall above. The grass roots into sediment that was once stone. The stone was once seabed. And tonight's cold may already be entering the next seam higher up, preparing more material for the same descent. That continuity prevents the basin from ever feeling finished. A mountain meadow beneath limestone walls is not the final resting place of the process. It is only one temporary expression of where movement has slowed enough to permit softness. The softness can be interrupted. A fresh spill from a couloir can reset a margin. A widened sink can draw water away and dry a patch. A wetter sequence of years can deepen grades upslope and increase fine sediment delivery downslope. Still, even these changes follow the same patient order. The mountain does not reverse itself. It continues opening, sorting, and redistributing. At the scale of one evening, all of this seems almost motionless. At the scale of many winters, the plain expands, old debris settles further, new debris arrives, and hidden routes of water become more established. At the scale of geological time, the whole massif is gradually lowered and partitioned. Passes open, towers stand out and then diminish, cliffs retreat, fans spread, soils deepen in places sheltered long enough. And through it all, the limestone remains recognizably itself. Pale, bedded, reactive to water, full of inherited lines. That inherited structure gives the process its consistency. Without bedding planes and joints, frost wedging would still act, but differently. Here, in this alpine limestone, the rock comes already prepared with planes of parting. Those planes are ancient. Cold is comparatively recent, yet cold has become the careful reader of those old lines. This partnership between origin and weather is perhaps the deepest calm in the whole landscape. Nothing is arbitrary. The mountain changes according to what it already contains. A final detail of the basin floor makes that especially clear. In a few places, older slabs protrude from the settled rubble at slight angles, as if half emerging. They have not pushed upward, of course. Rather, finer sediment has been removed around them or has settled more deeply beside them. But the effect is striking. A buried bedding plane reappears. A fragment of ancient seafloor geometry returns to sight from within an alpine deposit. The plane quietly reveals its layers. Not just material layers, but temporal ones. Marine deposition, lithification, uplift, jointing, freeze-thaw opening, rockfall, sorting, soil formation, rooting, hidden drainage, all present in one small patch of ground, and yet the place remains restful. That is the strange gift of these mountains. Their complexity does not demand urgency. It invites stillness. You can sit on an old limestone block at the edge of the fan and let the basin settle around you. The cliff above no longer feels severe. It feels patient. The scree does not feel chaotic. It feels arranged by long repetition. The dark seam under one moss patch does not feel secretive. It feels dependable, a place where water has passed often enough to leave a memory. Even the cold entering the ground after sunset feels familiar now. It is simply the next phase beginning again. Somewhere above, a damp joint is narrowing with ice. Somewhere in the old fan, a fine support is shifting under a small stone. Somewhere at the meadow edge, moisture retained by roots will freeze when night deepens. None of those changes needs to be seen directly to belong to the same story. The story is visible already in the forms left behind. And because those forms remain, the next winter does not begin from nothing. It begins from a mountain already edited by all the winters before. That is why the Alps limestone keeps its distinctive look across whole massifs. Not because every wall is the same, but because the same kinds of structure and climate keep meeting one another. Pale ridges, sharp towers, broken passes, deepened grikes, wide scree basins, quiet turf at the margins. Each feature is a sentence in the same long account of rock yielding by increments. As the cold strengthens, surfaces begin to simplify again. Damp patches darken against pale stone. Moist seams become more legible for a little while before full night absorbs them. The newer debris still stands out, brighter than the weathered ground around it. That brightness is a reminder that the transfer is ongoing tonight, not merely historical. Some fracture higher on the massif has already been widened this season. Some small block is more detached than it was last autumn. Some seep entering the limestone pavement has chosen a route that did not exist or did not matter a few years ago. The mountain continues to sort itself. From this lower ground, the larger silhouette above remains steady, but you know now how much quiet difference is concealed inside that steadiness. A ridge keeps its form by losing details. A tower keeps its outline by surrendering fragments to the fan. A pavement keeps opening because water and cold return to the same lines. A meadow edge keeps forming because enough old stone has rested long enough to be softened into a finer substrate. This is what the plain of broken stone teaches most clearly. The mountain's beauty is not separate from its reduction. Its calm is not separate from motion. Its stillness is built out of repeated change. And because the change is patient, the result feels ancient even while it continues. Soon the basin will be all grey and silver under the night sky. The pale limestone will hold the last of the